Okay, so this is the first example from your notes today. We have a 16 millimeter diameter steel rod 2 is connected to a, sorry, I don't know why it keeps getting out of zoom. There we go. To a 50 millimeter wide by 8 millimeter thick rectangular aluminum bar. Determine the force P that's required the assembly to stretch 3 millimeters. So the first thing I always do is organize my data. So we have rod 2. So this is steel. And we're given E equals 200 times 10 to the 9th pascals, because I like to keep everything in terms of newtons and meters, so I don't have to worry about conversions. And I also know that the diameter is 16 millimeters, so 0.016 meters. Area is pi over 4d squared, and that'll stay in meters. Then we have a rectangular bar that's made out of aluminum, and it has an E of 70 times 10 to the 9th pascals, which is a newton per meter squared. Determine the force P, that's unknown, required to stretch the assembly. So as I load this, I'm going to get a translation, okay, and it is going to be some delta, so that I have a change in length of A to B and a change in length of B to C. So I know that my delta at C is the change in place of A to B plus the change in length from B to C. Okay, so we have our material properties. Oh, Meg, stop eating paper. Okay. Sorry, I gave my puppy peanut butter jar to chew on, and she's eating the paper. So, okay, so we also have an initial length here, an initial length here. And then we said the cross-sectional area of 0.05 meters by 0.008 meters. So everything is listed. And we know that we need to find the change in length of A, the change in length of B, and together those should equal 0.003 meters. Millimeters. Okay? So the first thing I always do is I start with a free body diagram and equilibrium. And when I see an axial system like this, I know I'm going to break it here, find internal, break it here, and find internal. And if you need to use your post-it note, come across, cut. So I'm going to have a free body diagram that looks something like this. I have an unknown load P. I have an internal force of B to C. And when I sum my forces, in the x direction, they have to equal 0. So I'm going to have negative FBC plus P equals 0. So I can find that the force that's in B to C is equal to P. And now I've got to come across because I need to figure out what is the internal force happening here. So I can pull my bar, draw a picture, have this in this external P. I'm going to have an internal force, okay? And it's going to be from A to B. And I'm not applying any other loads externally. It's just this force P is being transferred. Okay. So when I do my summing forces in the x direction equals 0, I get that the internal force of A to B also equals P. Okay. I know delta is PL over AE plus PL over AE. And these are associated with A to B. This is B to C. So now we look at deformation. We always start with equilibrium and then we look at deformation. So I have delta C is 0.003 meters. And this is going to be the sum of my deltas, which is delta A to B plus delta B to C. So we can set that up. 0.003 meters equals, okay, we're going to sum up. Let's start with A to B. Well, the force in A to B is equal to P, so I can P. Its original length is 0.45 meters. Its area is 0.05 meters times 0.008 meters. Okay, and its E is 70 times 10 to the 9th pascals, which is a Newton per meter squared. Equals. So I've got meters, meters, newtons, meters squared. Now we need to add B to C. So plus, okay, the internal force from B to C is related to P, 1 to 1. So I have P. Its original length is 1.30 meters. It is a cross-sectional area of a circle, so we have pi over 4, 0.016 meters squared. And then we have a modulus of 200 times 10 to the 9th pascals, Newton per meter squared. So everything I have is in meters, pascals, Newton per meter squared, and my units are working out. So I'm going to simplify, and I get 1.607 times 10 to the negative 8th p plus 3.233 times 10 to the negative 8th p. And I can add those up. 4.84 times 10 to the negative 8th p. And then I can do my algebra, and I can calculate that p equals 61,984 newtons, which is 62 kilonewtons. And that would be the force P applied to the system that would provide me with a displacement of 3 millimeters, which is 0.003 meters. Really, these types of problems, it's information organization, and it's understanding how these, how all of these variables are related for each material, and then putting it all together for the big picture.